Welcome, everyone, to the second day of the Energy and Nanotechnology Storage in the Grid Conference. I'd just like to introduce myself. I'm Walter Chapman. I'm a professor in the Chemical and Biomolecular Engineering Department here at Rice. I'm also director of the Energy and Environmental Systems Institute. The Energy and Environmental Systems Institute is one of the co-sponsors of the conference, along with the Center for Nanoscience and Technology and the Baker Institute. Just to give you an idea of what the Energy and Environmental Systems Institute is, let me begin by just talking a little bit about what we do. The Institute is involved with taking faculty members' ideas and really promoting those, developing and these ideas are related to developing new energy solutions, as well as environmental solutions and environmental policy. The Rice faculty are, first, Rice University is small, but Rice faculty are well known for working on large problems, really the big problems facing society today. So the scope of the Institute involves several areas. One is, of course, research of the faculty. It's cross-disciplinary. It really brings together all faculty members from all over the campus, from the sciences and engineering to the economics and humanity, as well as, of course, the Baker Institute for Public Policy. The idea is that we promote or provide opportunities for these faculty members to interact, to network, not only within the university, but outside the university, as you will see. So I should start off by saying that energy and energy solutions, I know that we're all aware that we should move away from hydrocarbon as energy as a fuel, really. But we also recognize that the energy pie is such, and the demand or growing demand for energy is such that oil and gas, conventional oil and gas, will remain of importance to the world for the next 10, 20, maybe 30 or even 50 years into the future. Just the ability to produce the energy that's needed, as of course the United States has growing demand, as well as you know, China and India are developing, is going to rely somewhat on energy. And so what we need to do is we need to provide research that allows us to more efficiently produce and develop and utilize this energy source, and also to minimize its impact on the environment. And so, as you might imagine, with Rice University being in the center of the energy capital of the world, we have a number of faculty who are working along with the energy companies in trying to develop this new technology. And so I highlight here in the area of exploration, we have there are a number of faculty, both in earth science as well as in our computational applied mathematics department, working on various imaging techniques and seismic. And I should say that the energy industry has always been a high technology industry. It's a very competitive industry, and so they're going to take advantage of any new technology that they can, from, of course, nanotechnology through high-power computational methods. But these are also cross-cutting technologies. For example, the imaging technology also moves over into the medical imaging field. Also in the area of production, we have a number of faculty working on using, for example, CO2 for enhanced oil recovery type research, as well as CO2 sequestration is of interest. And I've listed a few others here related to, for example, flow assurance, which is essentially maintaining the flow, preventing plugging of pipelines due to various things that are contained within the oil. And in addition, we're, of course, what I've talked about really is the upstream. We're also focused on the downstream, which includes the refining, but also the manufacturing of various chemicals. And so, again, there are a large number of projects and interest of the faculty in this sort of area. But the faculty, of course, are also involved in emerging technologies, or say alternative energy type technologies. And I'll talk about a few of these. There's fuel cell membranes. We have faculty, Andy Barron and Mark Wiesner, are working on developing new catalyst technologies for fuel cells and new membrane technologies. There's work going on in hydrogen production, solar energy. In biofuels, actually, one of my graduate students, Matt Yarrison, as well as Catherine Robichaud, who's actually one of Mark Wiesner's former students, have actually taken it upon themselves to form a biofuels club at the university, where they've designed a way of converting the waste oil from our kitchens into biogas, biodiesel, that's going to be used in the facilities equipment, for example, lawn mowing, as well as the shuttle buses that go around the university. So I think it's pretty incredible just what not only the faculty but the students are capable of. Of course, there's other interest in robotic systems, which have application both in biomedical type applications, but also in oil and gas production. There's analysis into the global carbon cycle, understanding how the climate is affected by the global carbon cycle, and what the global carbon cycle has been over the last few million years. Of course, there's other research in, for example, methane, but also in the area of economics and policy and understanding energy supply, energy demand, and also the public policy that should be involved with this. So I've tried just to give you an overview. The Energy and Environmental Systems Institute, which we call EASY for short, EASY spans 6 schools in the university, from engineering, natural sciences, School of Sciences, architecture, humanities, management, and of course the Baker Institute for Public Policy. And I should emphasize that what we're trying to do is to promote the ideas of the faculty members, because all the institutes here at Rice are really driven by the interests and the capabilities of our faculty. There are other affiliations that that EASY has within Rice. Along with the Baker Institute, for example, we established the Rice Energy Program. Along with through Shell, we established a Shell Center for Sustainability. And there are of course, other centers and programs that have us interacting within the university, but also with industry through a couple of these industrial consortia that I list at the bottom. And to talk about the alliances that we have outside the university, we're currently working with a number of groups, leaders in business, including the Houston Energy Collaborative, the Greater Houston Partnership, University of Texas, the Bureau of Economic Geology, in their FutureGen efforts to bring a zero-emission energy or electrical power facility to the state of Texas. We're also working with international groups like in China, the Nankai Center, and also in France. So there's continual efforts throughout the university to focus on the large problem of energy and the environment. Now, I'll just say a couple of words. Yesterday, we heard a number of excellent talks on the electrical system, electrical grid. This morning, we have another tremendous lineup of speakers, many of which will talk about energy storage and distributed energy. And so I'm real excited to get us started, and I'll hand it over to Peter Hartley to introduce the first speaker. Thank you.
Thank you very much. We're going to begin our day-to-day discussing again some policy questions. And one of the most interesting things that came up yesterday, I think, was the discussion we had at the afternoon about how we move from a lot of the technology into getting the technology actually being used, and can we shorten the amount of time it takes to do that. We have a similar issue in the policy area. As I mentioned, economists have been talking about using much more market mechanisms in the electricity sector for at least 25 years, if not longer. But anyway, I'm very pleased this morning we're going to have a real expert, Frank Wallach from Stanford University, to speak to us about some of the issues that were raised yesterday, speak in some more depth. Frank actually is coming back to Rice in a sense. He was an undergraduate here. So I'd like to welcome Frank back. Thank you very much.
I will be very much giving the economist's perspective in terms of as the title of my talk is the benefits of load as a strategic resource. One of the things that I think is missing in virtually all the wholesale markets that exist in the United States, where, as well as around the world, is this piece, and in many ways explains much of the problems that have existed with electricity industry restructuring. So the idea is really just to give you an idea of how demand can be an active participant in the market and where the benefits from it being an active participant in the market come from. The next is to at least try to explain to you why this hasn't happened. In some sense, it really is an outgrowth of the regulatory structure we have in the United States, as well as just, I think, history, and that there's a lot of inertia in the system. And then the other is to try to explain to you that what I like to call symmetric treatment of consumers and producers is essentially common to all markets. It's only when we have a regulatory structure that we can really shield consumers from the essentially prices that exist in the market and give them what I'll explain is a free option. And free options, as we've learned in California, are extremely valuable, but they have to be paid for by the consumers eventually. It's just either in their role as taxpayers or as consumers. And so the other is to just emphasize the distinction that I think is often confused, is that it really is real-time prices that people need to see, not time-of-use prices, and I'll make that clear. And the other is to avoid, as much as possible, load profile billing, and really focus that only on what I'll call default customers, customers who never leave their incumbent supplier. And then I'll talk about kind of two ways that load can be beneficial to the market. The first is sort of as a passive participant. In the economist vernacular, this would be load as a price-taking market participant, similar to a generator as a price-taking market participant, just saying, look, I'll bid in, I'll sell whatever the market price is. The other is load as a strategic participant, and unfortunately, this is really where there's almost nothing going on, even almost nothing going on in the United States in the first one as well. And I guess that finally I'll just end with a provocative statement that I think that that restructuring will have been not the certainly something to have earned consultants a lot of money, but I'm unclear to the extent to which consumers will have benefited if we don't get the demand side involved. And so the idea is pretty simple. It's just things that as a former Rice engineer, I can say engineers don't like, but economists like, is that, essentially high prices cause people to move from purchasing the thing that's costly to the thing that is cheaper. And similar mechanisms can operate in electricity. And one of the big problems that people always say is, but I need this electricity in every single hour. Well, you can solve that problem by the fact that you purchase in advance the essentially demands that you know based on expectations, and then you can essentially be a spot market participant for what your consumption is at the margin. So in other words, you purchase 100 kilowatt hours for 24 hours a day, 7 days a week, and when you don't need it, you sell it, and when you need more, you buy more, but you buy more at the spot price. So what is the regulatory structure in the United States that leads us to have this very difficult problem of getting the demand side involved? It's this separation that we have in every state but Texas between federal, essentially wholesale market oversight and retail market oversight. Wholesale is the domain of the Federal Energy Regulatory Commission, and it has this mandate that have to make prices just and reasonable, which is certainly a very high standard, and many would say impossibly high standard for electricity. And the other is that the state PUC have control of retail prices. And in the old regime, this worked just fine, because what happened was that essentially the utilities that were located in the state essentially owned all the generation necessary to serve their demand, or had long-term contracts for this energy. And so what happened is that basically, even though FERC did regulate wholesale markets in the United States, it really didn't do anything, because essentially the state did it through the fact that the procurement policies for retail prices. So essentially, the states controlled retail prices in the vertically integrated regime. Well, that changed when you restructure. I mean, in some sense, one of the big things that restructuring has done is shifted control of electricity prices from the control at the state level to the control, if you like, at the federal level, or hopefully through market mechanisms, because basically the problem is that when you're purchasing a significant amount of energy from a wholesale market, you, the state regulator, can't say this is what the price has to be. Your only choice is turn the lights out or pay the price that the wholesale market is charging. And, you know, so one of the big problems that we run into is that the issue, another factor leading to this sort of reluctance to let customers see the prices, is that this really could be perceived by the regulator as giving up regulatory authority. In other words, letting customers manage the wholesale price risk is, in some sense, could be perceived by the state regulator as essentially giving up their authority to control retail prices. But I guess what I would say in response is, see the first line on this slide. In other words, once there is a wholesale market in your state, you don't have the ability to control retail prices, so you might as well I guess, allow customers to get in there and do what customers do in virtually other markets. And as we'll discuss later, there's a significant cost to preventing consumers from managing wholesale price risk, because basically, you know, you still have to pay for it. It's just that you don't have the benefit of being price responsive. It would almost be like you fly on all the airplanes that you fly on, and then at the end of the month, the airline sends you the bill for the planes you flew on, and you still have to pay it. You just didn't have any ability to determine which flights were cheap and which flights were expensive. So what is this sort of asymmetry in how load and generation is treated in most wholesale markets? Well, in all wholesale markets, a generation owner can essentially benefit from increasing its output in response to hourly electricity prices, or reducing its output in response to hourly electricity prices. So this would be the sort of passive, not strategic attempt to influence the price, but they also have the strategic ability to influence the price by basically reducing how much they supply, or bidding higher or bidding lower. They can influence the price as well. Well, a retail customer essentially has no ability to do that, because, as you know, just to give the example of California, but this is no different from any other market in the United States, is that regardless of the wholesale price during the hour, I only save 13 cents for every kilowatt hour not consumed, regardless of what the price the kilowatt hour is during that hour from the wholesale market. And moreover, I certainly have no ability to alter the hourly price by strategic behavior. In other words, by how I bid my demand in or into the wholesale market. And, you know, essentially, as I said here, is what loads currently pay is a constant over time and space, and unfortunately the state regulator in most markets allows you to switch back to this default rate at any time you'd like, and this sort of free option to buy at the default rate is extremely valuable. In other words, whenever, as I'll show later, whenever it's favorable for me to buy at the default rate, I'll do that, and whenever it's not, I'll go back, which can create an enormous liability for the state, which is where we are in California. So, you know, when in contrast, generation owners essentially will be paid the wholesale price at their location. And if they don't want to pay that or be paid that, they can sign a hedging arrangement. And so essentially the same sort of thing has got to occur in electricity, because if we can do that, in other words, treat producers and consumers symmetrically, just like we do in every other market, you know, in the airline industry, the airline doesn't, you know, there isn't a mechanism that holds out seats on the airplane at some, you know, cheap rate for customers. It's, you know, buy when you buy, pay what you pay at the time that you buy. What we can get is really consumers as what I like to call is negawatt suppliers. So if we see D of P is my hourly demand as a function of the hourly price P, then essentially taking the difference between my demand at a price of 0 minus my demand at a price of P, we effectively get a upward sloping supply of negawatts. In other words, that's my willingness to supply negawatts, just like it is, and it looks just like, from the purposes of the market market maker in the wholesale market, it looks just like a supply curve of energy. It's just that I'm supplying megawatts, reductions in energy, as opposed to I'm supplying actual megawatts, but in some sense, to the extent that it's just as responsive as a generator, it does the same thing in terms of reliability. So what should be is essentially the default price for that reason that all customers should pay is the hourly price. In other words, the price that's cleared through the real-time market. And if I want to avoid that, just like if I want to avoid the spot price in the airline industry, is I make a reservation in advance, purchase my ticket in advance, buy a forward contract, hedge that spot price risk, because the spot price risk in the case of airlines is I could either be stocked out an infinite price, or I could be just having to pay whatever the price is the day that I travel. And this sort of hedging of spot price risk is commonplace. I just list some examples right here. It's just that it doesn't happen in electricity because of the reasons we discussed, is that it didn't make a whole lot of sense in the former regime, but now it does. And so essentially the idea is that the real-time price really should be the default price for all large customers. These, after all, are very sophisticated customers. They need to have the hourly metering technology. We'll talk more about that. Residential and small business customers that elect to exit, they should also face default as the real-time price risk and have an hourly meter. And once they leave, they can't return. That free option is just too valuable. The regulated retailer can essentially maintain, if you like, the old paradigm, which is I'm going to manage the spot price risk on behalf of the customer, but essentially, and hopefully try to provide an incentive for people to take on this real-time price risk. But essentially, and this is just a way to address the question of it may not be beneficial for everyone to have hourly meters. And in that sense, you just say, okay, if you stay with your default provider, you can essentially continue to be provided with this spot price risk management services, which is what we used to do in the former regime. We just said, look, you're the vertically integrated utility. You manage this spot price risk for us. You send us the bill. We pay for it on a sort of an average price basis. Now, the other is that real-time pricing is what you need, not time of use. Reason is quite simple, is time of use just replaces one fixed price for every hour with two fixed prices, one in the peak period of the day, the other in the off-peak period of the day, but it's still a fixed price that doesn't vary with essentially real-time system conditions. And so it creates all the same incentives of a fixed price, and in many ways doesn't buy you much more in terms of market efficiency or system reliability benefits. In other words, you destroy that negawatt supplier relationship that we talked about, because demand is a function for the consumer of the TOU price, not the real-time price, and you want to put through that real-time price to the customer to get them to essentially either say, okay, I'm going to buy out of facing that price through some sort of hedging arrangement, or I'm going to buy out a part of it and then manage some of it at the margin. And the other is load profile billing, and this is another one that has some very perverse incentives. Essentially, what you do is you take a typical weighting scheme for a customer. So the WHD is the weight for hour H of day D. Price is the wholesale price in that hour H of day D, and you compute the customer's monthly bill as essentially the monthly consumption times this load profile weighted average of the hourly prices. And this, once again, has the problem of the customer gets the same benefit from reducing his demand in the middle of the night, when you really could care less if he does, versus if he reduces his demand when the hourly wholesale price is $250. I mean, what you want to do, once again, is put the signal to reduce at the time that you want the customer to reduce, to get essentially get the negawatt supplier mechanism to work in your favor. So, the interesting thing is that we would never think to do such a thing in another industry, network industry, that we've introduced competition, which is the long-distance industry. Imagine load profile billing for long-distance calling, where what you would do is you'd say, tell us what your profile of long-distance calling is, and then we'll give you a load profile, calling profile, because all we can do is measure the total minutes of phone calls you make in a month. Well, you'd have just an enormous, cross-subsidization problem, because essentially, clearly a call from, Houston to Paris is going to be much different from a call from Houston to Paris, Texas. And so, it's going to be, and if all you can read is the total number of minutes that customers made of phone calls in the month, you don't know, how expensive those minutes are in terms of, the network services that they're being provided with. So we don't think to do it in telecoms. We certainly shouldn't try to do it in electricity. And the reason is just simply this fact, is that under regulation, the sort of system lambda, highest marginal cost unit operating in the hour, probably under regulation, within the day was probably about 5 to 1. In a wholesale market, that can be as high as 10,000 to 1 in the case of the Australian market, which currently has a bid cap of $10,000 per megawatt. So you can have a price in 1 hour of the day that's $1 or even negative. And you can have a price that's $10,000 in another hour in the day. So there's a significant sort of welfare loss in terms of the fact of, that you're having someone consume something that clearly they don't value at that price during that hour, and because you're averaging the price signal that you're sending to them. And moreover, we would never see negative prices for electricity if you actually let customers pay the negative price, i.e. be paid to consume electricity. And so, because what we're essentially trying to do in those instances is get suppliers to go away. And one way to get suppliers to go away is also to get demand to increase in those half hours. So very quickly you'd eliminate those negative prices, which are fairly common in virtually all markets. The other issue is the question of, well, you need this metering technology to make this whole thing work. And the nice thing is that the price of this technology is falling. And moreover, just to give an example from a company in the Pacific Northwest in the Seattle area, Puget Sound Energy, serves about 500,000 customers. And their argument is that just on the fact that it saves in meter reading cost and dog bite cost and other sorts of things, their argument is that it's a wash just on the basis of that, meaning that the cost of ubiquitous metering throughout their entire system is roughly what it costs them to replace the meter reader. So in that sense, I think it certainly makes a lot of sense just to install it, and it gives you this increasing households with access to the internet. And there certainly is a growing interest in this throughout the United States. The big issue is to get actually the regulators to allow people to see the price. I mean, one of the more depressing things in Puget Sound's case is the fact that they installed this, and the best they could get from their regulator was a time of use rate where the difference between the peak and off-peak period was probably about a ratio of 1 to 1.5, meaning the peak period price was about 1.5 times higher than the off-peak price. Customers just aren't going to respond to that. So can active demand benefit the market? The interesting thing is that in California, we have evidence that essentially something really, 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 really dull worked fantastic, in the sense that California implemented this 2020 program, which said that if you reduced your consumption by 20%, you got a 20% rebate on your bill. Roughly 1/3 of California customers qualified for these rebates. This was an extremely dull price incentive, got demand to really reduce, unfortunately just total demand for the month, not when we actually needed it. But basically, despite this evidence, we still have no real-time pricing programs in California. There's lots and lots of studies and experiments, but still the regulators don't believe that people respond to prices. So this is just to give you an illustration of the fact that people will respond. And the illustration of the free option problem is that the blue line is the one that's of interest. This is the number of customers in California taking what you would call as a direct access service. And what happened is that the peak here that you can see occurred roughly in the summer of 2000. And when wholesale prices started to go very high, more favorable terms were available at the default rate, so if you switched off. And then where you see the trough down there is at the height of the crisis in January 01, essentially everybody said, gee, we can buy a direct access at a very high price, or we can essentially go back and buy at the default rate. So everyone went back and purchased at the default rate. Then where it heads back up is the state during the winter of 2001 purchased the forward contracts to essentially serve all those customers on the default provider rate. And that settled down the spot market, and sure enough, everybody went back then to purchasing at on the default rate, because now the spot price was a better deal. So this is just an example of the fact of what can happen with retail customers. So this is actually my consumption. The only sort of benefit that I realized from being a shameless advocate of getting the demand side involved is the company that actually installed the meters asked me if I wanted one, so I said yes. And so what I can do is at least record my consumption. And the only point that I really want to make from this graph is that first, if you stand in front of your meter, because these are remotely generated by a telephone, you can block your consumption, which is why my consumption was 0 at that point. It really wasn't. It's just standing in front of the meter. But the idea is to just demonstrate to you, see how peaky my demand is. And this is also, I live in the Bay Area where there's no air conditioning, and at least at the residential level. And so much of this stuff is stuff of just doing what you might call as foolish things of consuming stuff that is at times coincident. And so you can see my peak demand for 1 hour is about 4.4 and kilowatt hours. Whereas if you go to the next week, you can see my peak demand occurs in the middle of the week, and it's only 2.8. So, so the idea for me would be I'm going to buy a sort of in advance a load shape for the stuff I know I'm going to use to run my refrigerator, to do the other sorts of things. But then at the margin, I'd be willing to take on some real-time price risk to save myself on my bill. And then the other is just to illustrate that if you go out of town for the weekend, it's a great way to be price responsive, because as you can see, the demand goes exactly, sort of right down to just what keeps the refrigerator running and those sorts of things. Okay, so how do we get active demand side participation? Well, the first thing is to treat load and generation symmetrically. Don't give out free options to customers, because they are sophisticated and they will respond to the extent you let them, despite what regulators may think. And the other is there's lots of low-hanging fruit. Just to give you an idea, is the total, if we take total annual energy demand in California, megawatt hours, we divide by hours, that means we've roughly got a capacity utilization rate of 2,800 megawatts. Total in-state capacity is 50,000 megawatts. So if we can just trim the peaks off with a little bit of demand response, there's a lot of we can avoid having to build a lot of new generation, as well as encourage the development of renewables and distributed generation technology. So now I want to just talk briefly about what's going on in some other markets that have been at this a little bit longer than the United States and are a little more rational in terms of how they involve customers. In the UK, they have what are called real-time pricing contracts, where customers are charged the half-hourly wholesale price for their customer consumption, at least the portion that is the wholesale portion, plus some sort of fixed transmission charge. And this just discusses some work that I've done on that for a sample of large industrial and commercial customers. This paper's on my website if you're interested, is we want to look at the substitutability. And the first thing that we see is virtually across all of the customers, there is price response. Now, true, it's differing levels. Like, for example, my favorite one is the water utilities, which are very much just all they have to do is pump water once a day. So for them, it's very much just like they pull the trigger whenever it is that the prices are cheap. And if you look at the system load shape, it's like this. If you look at their load shape, it's like that. In other words, they're looking to consume at the lowest price periods of the day, and they're very good at it, and they're very good at moving around what they do. And, so this just, we show that if you just had these guys, that demand response passively bidding into the wholesale market could significantly limit price volatility. And what we mean by passive bidding is just to say bid in the demand curve. Don't use this demand curve strategically, as I'll discuss in a few minutes. And the other thing is just to notice is that, just to give you an idea of how good some of these guys are, is everybody faces the same half-hourly pattern of prices. So think of it as that everybody faces the same mean price for the year in terms of sample mean, sum of the P's divided by T. But everybody, the people that are particularly good are those who are able to buy in the lowest price periods their consumption. So think of it as we can rate people by their quantity weighted average price, which is we'll call P average. And just to give you an idea, here's 1991, 1992. Prices are in dollars or pounds per megawatt hour, and this is the half-hourly pattern of prices. And then this just gives you the histogram across essentially 350 customers of their quantity weighted average prices. So in other words, some customer was very good and managed to essentially consume during the lowest price period to get their quantity weighted average price down to about 19. Somebody else wasn't so good, had to purchase primarily in the peak period, and theirs was about 31. but the vast majority was near the time-weighted average of prices, which was about, in this period, 25 pounds per megawatt hour. So now the interesting thing is just to illustrate to you, this is now a much more volatile year of prices. So now the question becomes is, what would happen to you expect to the support of those quantity-weighted average prices? So this sort of says, look, you know, what you call volatility and a terrible thing, I, as a real-time pricing customer, call an opportunity, because that tells me I can purchase in a lower price periods than you can. And sure enough, if you look, is you know, the support, it goes from roughly about 21 to 40, so a range of about 20 versus a range of about 10 when the volatility was much less. And it's also true that average prices were also higher, closer to about 30 pounds per megawatt. So in some sense, the price volatility is a source of value to the real-time pricing customers, and those who are particularly good manage to reduce it. So the final point I just wanted to talk about was you can even use real-time pricing to exercise, if you like, buying power on the demand side. And the way you do this is, first, you don't, that's a summation sign, but the idea is that you use your real-time pricing customers as a way for the buyer to exercise monopsony power. How does that work? Well, what I do is I make the promise to my real-time pricing customers that you will pay, on average, the same price for the month as the wholesale price for your power. So in other words, the real-time price that I charge you times your consumption summed over all hours of the month equals the wholesale price that I purchase at times your consumption for that hour summed over the entire month. And I will give you a share of the savings that you being price responsive gives to me. How that works is essentially during the high price periods, I'm going to send you a very high price to get you to reduce, so I can reduce my purchases from the wholesale market, the price I have to purchase at. During the low price periods, to make up, I allow you an even lower price to get you to essentially consume more to replace that. And so the idea is pretty simple, is, okay, this would be demand. Q0 is demand without the RTP. QM is the demand where I get the price responsive customers to go away. This reduces what I have to pay to serve all of my customers. That's the blue area there. And then to make up for it, I essentially increase demand in the off-peak periods by essentially cutting the price to the RTP customers. That increases my wholesale price just a little bit, but you can see the one blue area is certainly smaller than the other blue area. So I, as the retailer serving some fixed price and some RTP customers, benefit. And so therefore I share some of those savings with you by essentially exercising monopsony power. And so just to finish up is just to say that it seems that unless we can get the demand side involved, it's going to be very difficult for us to realize much benefits from restructuring, because the problem is we're doing a pretty good job to begin with. And the simple idea is just, we could say, look, by getting price responsive demand in there, we can essentially run the system with a lower level of capacity, make more efficient use of that. And the simple way to think of that is the airline industry is regulation. We had load factors of about 55%. Currently, we have load factors in the high 70s. That's what's allowed us to have average revenue per passenger mile fall since restructuring. And it works because we have an active demand side. And without that, I think that it's going to be very difficult for a wholesale market to essentially beat the old, very, at least not greatly, very well regulated, but pretty well regulated former regime. Thanks.
Do we have any time for one question, or any questions, or we wait, do the second speaker first? We've got Roger Levy. So we're going to continue the discussion of real-time pricing. I think one thing that, one question I might get Frank to talk about, think about if you've got some time, is to lead into the next session, maybe give some comments on the effect of real-time pricing on incentives to put storage in place. All right. Introduce the next speaker, Mr. Levy. Thank you very much.
Good morning. Contrast to the bio that's presented in your packet, today I'm representing the Demand Response Research Center. I'll introduce what that is in just a minute. What I'm going to do is sort of add some fur to the dog that Professor Wallach introduced just a minute ago, and cover what California is actually doing in the demand response area, specifically with regard to the policy, pricing, and technology initiatives that are underway that are an attempt to actually implement the various things that Frank just introduced to you. First, just a few brief comments. The energy industry is often considered synonymous with advanced technology, and the discussion that took place yesterday in this room could only be characterized as advanced technology. It's so advanced, in fact, that most regulators have no idea what you're doing in the research labs. However, while high tech is relevant to generation, the demand side, or how the customer interfaces with the utility, how the customer interfaces with the system, hasn't changed much in the last 80 years. This is the problem with demand response. And in fact, to emphasize what Professor Wallach just said, is that I'll give you the basic conclusions at the beginning of this talk. There are no technology barriers to demand response. There are no behavioral barriers to introducing price to support demand response. The basic barrier to demand response is a policy and regulatory barrier. And what I'm going to show you later in this presentation is some evidence that is actually very consistent, has been around for about 25 or 30 years. It keeps getting reinvented every year with new pilot programs and new research. But what we're hoping that you can help do is find a way to convince the regulators to now act on some of this information. So the result is that demand response today is not much different than it was about 30 years ago when the first major programs were introduced by the federal regulation called PURPA, Public Utility Regulatory Act. And my goal today is to highlight some of the initiatives in California that we hope will change this perspective. Page down. A technology problem. Oh, this page down. Okay. So I'm going to identify critical problems that keep demand response from becoming a significant system resource. And then I'm going to identify the policy initiatives that California is pursuing to establish this. First, the Demand Response Research Center. The Demand Response Research Center, this is not a plug. It's basically the sponsor of my talk today. I'm an independent consultant. I've been working in the power industry for about 30 years. I am under contract with the Demand Response Research Center. In fact, they even gave me a title. I'm the Program Development and Outreach Manager. In that capacity, I've helped them develop their research plan. The Demand Response Research Center was created by the California Energy Commission about 2 years ago to bring together the research and development necessary to more systematically improve and facilitate the implementation of demand response. And so our research goals are really very short-term in contrast to what you were discussing yesterday. We're dealing with issues that are probably 2 to 3 years out, and our goal is implementation. But in that capacity, we also have to interface, and we are charged with interfacing with 4 other major research groups. The group called CSEM, CSEM, when you see on the lower right-hand side, is the Center for the Study of Energy Markets. This is basically research on energy policy. And for some of you who know him, Severin Borenstein, an economist, is in charge of that research group. CERTS, which is in the upper right-hand corner, is the Consortium for Electric Reliability Technology Solutions. And they're doing research to figure out how to better protect and enhance power system reliability. PEER, in the lower left-hand corner, the Public Interest Energy Research Group, is basically a research arm of the California Energy Commission. They fund research in generation and building and appliances in support of the building and appliance standards and the technology standards that the Commission supports. And finally, the one group that's probably most relevant to many of you in the audience is called DRETD, lots of different acronyms and initials here, the Demand Response Enabling Technology Development Group. They actually do hard science research. The function there is to look at research that's 10 years out that will produce hopefully 10 times the benefits, reduce the cost by a factor of 10, to develop enabling technologies for the long term. And I'll give you some examples of some of what they're doing a little later, and also announce very early on that we have, as a result of a lot of the research going on with all these groups, the opportunity to encourage you to contact some of these groups and collaborate in some of the research. We also have separate funding available for some of the research. So the problems with demand response. Let's get into the details. In California, the 12-month period from May of 2000 to May of 2001 brought home to all the customers in that state the structural problems with demand response. For those of you who don't remember, during that 1-year period of time, there were approximately 50 system rotating outages, and the state encountered roughly several $100 billion worth of lost product. and cost for commercial, industrial, and residential customers when their power was shut off. So there are several questions that were asked as a result of all those incidents, which actually motivated the formation of the Demand Response Research Center and a lot of the research that I'm going to present to you today. The first was, when prices increased by a factor of 5 in a very short period of time, why was there no reduction in peak demand? Because the customers never saw the price. Second question, utility outage management plans. For those of you who aren't aware of them, is that when utilities are faced with shortages, they actually have a plan that they keep on file with the regulatory commissions, which identify how they will rotate out certain segments of their grid in a random process to equalize the benefit to the consumer of not having power. So how do you solve the outage management practices that in California result in 50% of the customers being exempt from that? And let me explain. Utilities don't control power at an individual customer level. They control power at the circuit level or substation level. And also their regulatory commissions allow certain exempt customers, public safety, police, fire, certain transportation users, are considered exempt because they provide an essential public good that will cause substantial damage if they lose power. So if you're lucky enough to be on a circuit with one of those customers, you also wind up being exempt from an outage. It turns out in California, during the crisis of 2000-2001, they discovered that 50% of the state of California was on an exempt circuit. That causes some rather interesting equity issues. Third problem, customer bill management. Professor Wallach illustrated this fairly interestingly, that no matter what you do as a customer, you really can't save very much money no matter what the price is in any given hour. The bigger problem is that how can you manage your expense or determine what the value is to what you buy without getting a price? And finally, there's an issue, something called a rate. If any of you have looked at your electric rates, and if you're like most residential or commercial customers, and in fact, if you're like most utility commercial representatives, you find that you can't even understand your rate. So given that situation, it's very difficult to be able to control your bill. And finally, we get to the question which is most important to everybody in this room, which is how can you turn demand response into a viable resource? So I'm going to summarize the problems into 3 areas because all these problems come down to these basic variables. Price. Without basic price information, customers can't establish a value function, or they can't make rational investment decisions. And so changing the price, and it's difficult to go into this in such a brief session today, but providing customers the price changes everything. It changes what they invest in terms of infrastructure. It changes the cost benefit of various efficiency options which are currently being promoted today. Rates, something that doesn't get discussed very often in these forums, is that customers don't understand their electric rates until you can come up with a rate that customers do understand and communicate the price. You're really not going to make a lot of headway. And finally, electrical systems and load as a resource requires that technologies and procedures be in place that make demand response instantly available. Today in the utility industry throughout all of North America and most of the rest of the world, demand response is considered a program. It's targeted to a select group of customers. It does not include the technology in most cases that allow it to be instantly available. And so in California, which had 20 years worth of investment in demand response, the crisis of 2000, they basically had none. The only resource they had was what they call a curtailable interruptible rate. And those customers didn't expect to be curtailed or interrupted as frequently as they were. And after that crisis, and what exists today, is that about half of the actual demand response resource exists today in California, as did prior to the 2000 crisis. So these are the questions that the regulatory commission set out to answer. Now, just one brief piece of background that's important to how I provide the answers to these is that I was also retained as a consultant to the California Energy Commission during the crisis, at the end of the crisis, to help them try to resolve this problem and prevent it happening in the future. So what I'm going to show you today are the research initiatives and the policy initiatives that have been pursued for the last 4 years that are now actually in the final stages of being adopted or evaluated, and how they are going to affect the state of California. So I'll let you go through these questions on your own so I can stick within the time schedule. Let me get to some of the meat. This is the research agenda for the Demand Response Research Center. It's targeted very clearly at addressing these load as resource questions and pricing questions and rate questions. The arrows that are pointed to certain research blocks indicate the research programs that we're pursuing right now that hopefully will be resolved within the next year. and that specifically looks at, we have just let contracts to look at developing new rates and look at rate concepts that are quite different from what is currently being offered in the industry, and also new studies to attach a better and more complete value on demand response. And I'll go into that in just a minute. And I'll introduce that concept with this rather complex diagram. For those of you that are familiar with power systems, there's something called a resource stack. And generally it looks at base load, intermediate load, and peak load. And one of the problems with demand response as a program is that it doesn't get evaluated on a asymmetrical basis with resource. And so we looked at all the research and did some additional research, and what we found was that the customer actually doesn't differentiate between demand response and energy efficiency. They can't tell the difference. What the customer really does is they look at their energy use, and they want to be able to know something and get information that allow them to reduce their bill and live their life according to what they choose to do. So what this graphic really displays is what we call the customer perspective of demand response. And this is actually now being generally accepted within the state of California among the utilities and the policymakers. And what it says is that demand response is really part of a continuum from the customer's perspective of actions they can take to manage their bill and to live their lives. So the three turquoise blocks in the middle, labeled 2, 3, and 4, really reflect the capabilities of demand response. And what's important here is how they match up to the block in the middle called valuing demand response. I'll simplify this by saying that the wholesale market really provides only part of the value and part of the price that needs to be reflected to the customer to fully value demand response. So blocks 1 and 2, basic service and what we call shifting or rescheduling, are essentially price-driven or value-driven demand response actions by customers. They don't affect the customer's behavior in great ways. They don't affect their comfort or service in great ways. The value of those two actions is determined really by the market, wholesale market. But as you move into the block number 3, or the partial end-use curtailment block, what we call partial end-use curtailment, what happens is that the value of demand response switches over from being driven by the wholesale market to being driven by the customer's value of service. And this is where real trade-offs occur, and where real investment decisions change. Finally, you get to the full outage, which is the ultimate in service from a utility, is when you can no longer meet the demand. You shut everybody's power off, and we're hoping the initiatives that we're going to pursue will avoid all these things. Now, the other critical piece on this exhibit is what we call the time perspective. And if you look at the right-hand side of the graph, as time perspective, many of these incidents or the need for some of these demand response options are very, very infrequent, both in any given year or in any given long-term period, say 10 years. So, for example, full outages in California were, prior to the year 2000, very, very infrequent, and generally they're projected to be no more than about 6 hours a year in a long-term 10-year time frame. So the time frame perspective really dictates in some degree what kinds of technologies you need and the ability to respond. So for end-use curtailment in block number 4, you really need real-time technologies to be able to respond, and I'll show you why that's relevant as we go forward here. So I'm going to switch a little bit of direction here. These are the 3 policy initiatives that the state of California is pursuing. Statewide implementation of advanced metering. This is advanced metering for every customer in the state of California. Advanced metering means meters that can be remotely read by a utility company without the need for someone to be on site. Meters that can produce hourly or more frequent interval information that can support better pricing. Second, critical peak pricing as a default tariff. What critical peak pricing is a compromise between basic flat kilowatt-hour pricing or time of use pricing and real-time pricing. Critical peak pricing combines a time of use rate, or as Professor Wallach characterized it, 2 fixed prices, peak and off-peak price, that may be seasonal, with a dynamic dispatched price that actually reflects an average of the market price at the time, and it may include an adder to reflect reliability or the customer value of service. The reason for critical peak pricing as a default tariff in the state of California is because it's a hybrid of time of use pricing and real-time pricing, and it actually captures about 80% or maybe 90% of the value of real-time pricing. And most residential and small commercial customers aren't capable of responding to real-time pricing, so this presents a practical alternative for trying to implement demand response. the third initiative, which will probably be of more interest to most of the people in this room. It's called Programmable Controllable Thermostats in Building and Appliance Standards. And more generally, what this is the first look at beginning to use technology and to build technology into white goods and into customer and commercial industrial customer facilities that can automatically respond to prices, to reliability signals, and to basically change the definition of the obligation to serve as California and most of the regulatory commissions have defined it for the last 100 years. So let me take each of these initiatives and give you a little brief background on where they stand. Statewide implementation of advanced metering. As Professor Wallach stated, one of the concerns with advanced metering is it's too expensive. Baloney. What this graph shows is that, and I've tried to simplify things here, this is just from the utility perspective. This does not look at demand response at all. And what it shows on the left-hand side is the technology that most utilities today look at, which is called AMR, which is a system that allows a meter reader to walk by a meter and hold out a device and either optically or electronically or in a very short distance scan what the results are from the meter and then take it back to the utility. Some utilities use what they call drive-by systems. A van drives down the street, activates a short-range transmitter, which reads the meter. That information cannot be collected in either in the level of detail or quickly enough to support critical peak pricing or real-time pricing. On the right-hand side, the advanced metering at AMI is the metering that Professor Wallach described. It's meters that can be read remotely, not by telephone and not ones you can stand in front of and block the signal from, but remotely and at 15-minute, 30-minute, hourly intervals or even more frequently. And what the prices as of and what the studies show as of about the first part of this year is that the cost for both those systems is really at parity. Even better yet, as part of the initiative in California, the 3 investor-owned utilities were required to submit business case analysis, basically economic studies of advanced metering in March of this year. 2 of the utility studies showed that advanced metering, just looking at their own internal operations, not looking at the value demand response, that advanced metering was cost effective on its face to begin implementation right now. In the case of Pacific Gas and Electric Company, just looking at the improvement in internal operating business practices and procedures, they could recapture about 90% or more of the cost of the advanced metering system just from changes and improvements in their own internal efficiency. If you add into that something in the regulatory community which is called the non-revenue requirement functions, simple example, what's the value of theft, reducing theft to a utility company? And the answer is, in a regulatory environment, 0. And the reason is because they collect their revenue regardless of how much is stolen. They just collect it from those people who choose to pay. If you develop a system which eliminates theft by attaching value to each individual customer, all that results in is a shifting of revenue between customers, doesn't change the revenue requirement, sort of a perverse issue in the regulatory environment in terms of business investment. But when you add the non-revenue requirement issues like theft reduction into these equations, then PG&E's numbers actually recover over 100% of their cost just from internal operating and business practice improvements. You add demand response into that equation, and it becomes extraordinarily cost effective. So advanced metering is not hindered by cost issues. It's not hindered by technology issues. There are regulatory proceedings in California that are currently going on. The first decisions for those cases will be made in March of next year. PG&E has proposed to implement 9 million advanced meters in their system to automate all their gas and electric customers. San Diego Gas and Electric has proposed a similar proposal. We'll have to wait and see what the regulatory commissions decide. Second, the major issue, will customers respond to price? So California did what is we now call the mother of all pricing experiments. It was a 2-year pilot. It was conducted between December, I think, years 2002, 2003, 2004. It involved about 2,500 residential and small commercial customers, a very complex experimental design at a cost of about $20 million. And so what did that study show? It looked at different rates, time of use rates, critical peak tariffs with various differences, and also use of technology and the value of information to the customer. So what did it show? It said system impacts. On average, for critical peak pricing, and this is not the most effective type of critical peak pricing, California would expect to see about 1,500 to 3,000 megawatts of demand relief. That equates to about 2 to 3% of the state's system-wide peak demand. Now, since that pilot has been introduced, we've also introduced a technology initiative, and I'll go over that in a minute, which would actually increase, for emergency purposes, the reduction or the ability to reduce statewide peak demand by almost 20% in terms of system emergencies. So demand response can have an enormous impact on the resource requirements of the state. Second conclusion, that dynamic rates actually encourage greater conservation and peak load reduction than conventional inverted tier or time of use rates. And finally, this is the piece that was probably of most interest. It's probably the softest in terms of the kinds of research you do, the behavioral research. And this was the most surprising to most utilities, is that the customers actually understood these tariffs better than they understood their existing tariffs. They felt they were more equitable, more fair, and they also thought that they should be offered to everybody. So I'm going to give you a few examples of, I'll attach some numbers, I'll put some hair on this dog, and I'll get through this pretty quickly. This is the summary of that characterizes the results from the different rate treatments. So what you see is that the very small purple box called time of use, TOU, time of use rates, on average reduced peak demand about 4%, a significant reduction, but not anywhere close to what was produced by what they call the critical peak rates. There were two critical peak tariffs. One is characterized as CPPF, which means that the critical peak price was dispatched during the entire peak period, 6 hours, and it was fixed. The critical peak variable was dispatched on a need basis, so it might have been 1 hour, 2 hours, 3 hours during the peak period, only as needed. And then we have the turquoise box with a 34.5% number attached to it. When you include technology, when you give the customer the technology to automate their response, what happens? And what you can see here is that the customer reduction in peak demand was increased by a factor of almost 3. What I've done with the orange block on the far right is highlight what actually happened on the most critical day of the year with the customers that had the critical peak tariff, the variable tariff, and the technology. And what you see is that they reduced their demand by almost half. One of the questions that the regulators have to deal with, because they have difficulty believing some of these numbers, is what some of the interveners say is, well, these rates ought to be targeted toward large high-use customers or customers with air conditioning because they're the only ones that can respond. Well, the study looked at that. What it concluded, as you see from this graph, is that it doesn't really matter what the customer looked like. Large customers, small customers, high-use customers, low-use customers, customers who own homes, customers who rented, customers who had pools and air conditioners, customers who didn't, high income, low income, all the customers responded. A significant conclusion to the study. Finally, how effective are critical peak tariffs from just giving customers incentives to reduce load at peak? So this study also included an analysis of that impact. And what you see here, the dark blue line, is the control group's load during a critical peak day. The dotted line underneath is there were two groups that had critical peak tariffs or had demand response kinds of tariffs. The dotted line represented customers that had controllable thermostats, remotely controlled thermostats, that were provided with a conventional demand response incentive. They gave them a fixed incentive for the year to participate in the program. Every time that the utility had a critical peak event or a critical event, they would activate the thermostat, lower the customer's temperature, or raise the customer's temperature, which would lower the demand by cutting the air conditioning off. So the dotted line represents what the customer's load on those programs looked like. The pilot study that California did took a sample of those customers and said, we're going to change only one thing. We're going to take away your fixed incentive for the year, and we're going to give you a critical peak tariff. And that's going to be your incentive. And now you're the one who dispatches your thermostat. We'll send a price signal, but you have to set up your thermostat to do what you want to do in response to the price signal. And so the orange line shows what those customers did. They basically doubled the load relief. So changing the way you provide the incentive changes the load impact that you get. And finally, again, the difficulties with the regulators, you try to convince them that this is not an anomaly, that this is consistent behavior. And so we provided results to them that show that in similar pilots with comparable groups, statistically provable and reliable information, that these kinds of results, the four purple blocks, represent the California pilot on the far right and the first pilot done with critical peak tariffs back in 1991, that the customer response over the last 14, 15 years has been relatively consistent year by year, no matter where the pilot was conducted. And these pilots were conducted all in different parts of North America. Another piece of sort of interesting information that the regulators always ask and people want to see is how do these critical peak tariffs affect customers' bills? I'll let you go through this presentation package on your own. I see my time is running out. Basically, about 70 to 80% of the customers, residential and small commercial, saved money on the critical peak tariff. These tariffs were designed to be revenue neutral, which meant that if they'd done nothing, half the customers would have paid more, half the customers would have paid less. That didn't happen. Customers understood the rates and took advantage of them. And finally, the issue of preference, which is customers overwhelmingly, commercial, industrial, and residential, have a strong preference for these tariffs. So now you might ask, why aren't the regulators approving these tariffs? And I don't have an answer for that question, unfortunately. Finally, technology initiatives. What's the state developing? This is, again, probably more of interest to you. Long-term development to reduce the cost of technology for control technologies. There is rapid prototyping going on right now for the first programmable thermostat that will be introduced in March. There is a regulatory proceeding also in place under the California's Business and Building and Appliance Standards to adopt programmable controllable thermostats as a requirement in the building and appliance standards for all facilities, which means that customers will have the technology to automatically respond to price should the PUC adopt the rate. And one additional piece is that those technologies will also include a non-overridable feature that will allow the state to drop air conditioning load in system emergencies in lieu of rotating outages. The decision being that partially reducing someone's load and imposing a slight discomfort for a few hours is much better than a rotating outage which drops everybody's load. So this is a list of some of the technology initiatives that are being pursued by the DRETD. Please take a look at some of these. I provide some contact information later in the end of my presentation. If you have an interest, there are outstanding, we call research opportunity notices, which would allow some of your research departments to actually participate in some of these research efforts. Finally, just a summary of the policy initiatives and what their purpose is and why they're being pursued. The advanced metering initiative, statewide implementation of advanced metering being pursued to facilitate pricing and support customer education. The critical peak pricing is a default tariff, which will hopefully integrate efficiency with demand response, create an integrated perspective for the customer. And then demand response becomes a condition of service for all customers. Programs will disappear. All customers will have incentives. And finally, the technology implementation is part of the building and appliance standards to facilitate both the marketplace and the customer ability, the utility's ability to affect a change in the way they manage their energy. Thank you.
Okay, so we've got a few moments for some questions from the floor. I guess one thing is I would invite each speaker to comment on the other speaker's presentation too, if you have anything to say.
Well, my comment on Professor Walnick's presentation is we totally agree with what he presented. In fact, he's been an integral part of helping to push some of the initiatives the state's now doing.
Do either of you have anything to say too about, is there any evidence around from some of these cases like the UK and so on of time of use pricing driving interest in storage technologies?
Real-time.
Real-time, sorry, real-time pricing.
Well, I guess I'd say is without facing a customer, there's no value in storage. I mean, and you know, the simplest way to describe it would be that a pump storage facility is not financially viable unless you can get a 2-to-1 price swing within the day, because that's basically, you got to be able to buy it at the cheap and sell it at the expensive, and essentially make up for the fact that you can't, you know, thermodynamics applies. So in that sense, I think it really makes the storage very viable, as well as distributed generation. In fact, one of the big sort of pushes that I've tried to make is that, look, for all the environmentalists who like solar energy, they should be strongly in favor of real-time pricing, because essentially, when is the price of electricity likely to be very high? Well, it's typically like to be very high when the sun's out shining and beating down on the roofs in the Central Valley, and you can get a lot of solar power there. So you could make that solar power very financially viable if you're selling back to replace power that's priced at $750 per megawatt versus power that's only always priced at about $50 per megawatt, and solar is never viable then. So in that sense, I think it's another source of benefits to essentially a default price that is the real-time price. The other thing I just wanted to comment on is that it's as someone, it's depressing because, I was smiling in terms of that the presentation, which I thought was excellent, is just the state PUCs in California right now think somehow they're suspicious of the fact that now the utilities are on board with interval metering, so they think that this can't be good for consumers. And so they're, if anything, probably, it seems strange, but they are sort of really pushing hard against these programs being implemented for the metering, which is really difficult to understand, is all I can say.
Speaking as one of the utilities, not California, but I think you're underselling the value of AMI. There's a whole category of application that's very pertinent to the discussion of this conference. The meter is also a very important sensor in terms of scaling and the implementation of smart grid, so that some of those costs and benefits that you indicated, there's even more value. And that's something that's emerging and beginning to be understood, I think, and we're struggling with it ourselves to create that value proposition business case. It's more than what you say.
Well, actually, the business case that the utilities were asked to do was very highly structured, and it was, again, focused it was structured differently than regulators usually look at it, because it was structured purely as a business decision, forgetting about demand response. And so that business case actually did include the value of the meter for things like outage detection and how it affects outage management,
Beyond that.
and for reliability and power quality issues.
Beyond that.
However, the utilities tend to be very conservative. And so when a company like PG&E comes back, and the history is that when we first presented the business case structure to PG&E, their first evaluation showed that they could recover at most about 40% of the cost of the advanced metering system. However, when they sat down and we pressed and they did it again, they came back with 90% coverage. And what I can tell you is that the utilities will be very conservative on the benefits, and they'll be very conservative on the cost. So they will underestimate the benefits and overestimate the cost, which is in fact the case. And so what we're looking at and some of the studies that have been done independently is that the metering should be, there should be with demand response about a 200% coverage at a minimum, so that you're looking at a very cost-effective implementation of technology.
Frank, one of the comments that you put up a number that were related to a New York study in your slides, and it's a bit misleading. The information, if I recall, was that you estimated that
I didn't. This was just a number
a study
I
that you
study.
got, well, that it was that the cost for AMR was $2 a point, and that $2 a point, I believe I saw in one of the slides.
They estimated $2 a month addition to the bill.
Yeah, and that somehow equated to the cost of the manual meter reading. In the case of Con Ed, the cost of the manual meter read is much, much less. So don't use that. It's a losing way to look at it. It's not just that. It's this other value.
I agree.
So
I was just saying that I think at least, as I said, this report emphasized that it was a wash based on just the things that Roger talked
It's
about.
not a wash. And that's been actually, thinking that way has been one of the impediments of why AMR wasn't implemented earlier and why the utilities weren't interested, because of that kind of narrow view. When you look at its functionality, AMR is not equivalent, or AMI definitely is not equivalent to just the monthly meter read. So that kind of thinking is what stopped in many cases, the implementation of AMI.
Yeah, no, I think it's Roger's point.
Yes.
Is that cost recovery, they'll do anything if the regulator pays for it. So
That's what makes it, that's in a regulated industry.
It could be completely uneconomic, and they'll do
Yes.
it if the regulator pays for it.
In a regulated industry, that's the only mechanism that the utility can do these things. There's no other way to get the revenue.
Just to emphasize another point is that the metering is really critical because it facilitates the interest you have in storage and in distributed generation. As Professor Wallach said, is that solar becomes much more cost effective. In fact, one of the research projects that's being done by the center is to reevaluate the cost effectiveness methodology that's been used by California and sort of promulgated all over the country, because it is basically flawed. It has undervalued these resources for many years. And in fact, the initial studies that we've done show that things like solar and distributed generation are much, much more cost effective under these critical peak or real-time tariffs than they are under existing utility tariffs or assumptions. And so what happens is that before it's really difficult to look at distributed resources or storage or any other alternative energy without first having a good view of what the customer will do and how they will change the demand on the system. And I think providing price to the customer and letting the customer respond to price first will establish what the real shape of the demand curve is and what the real cost of the system are. And that really has to be determined almost first before you can properly evaluate a lot of the alternative energy investments.
Well, I think that's sort of a great point to end on, to have our break, and come back after the break and talk about storage technologies.